We just saw the idea of a one-to-one function expressed using functions with finite number of elements. Let's go ahead and look at the general definition. We say a function f is one-to-one if for all x1 and x2 in the domain of f we have that f of x1 is equal to f of x2 implies that x1 is equal to x2. Let's go ahead and check this concept geometrically. So suppose we have the following two graphs here. Let's go ahead and just determine by definition which one's one-to-one and which one's not one-to-one. We'll go ahead and start with the one on the right-hand side. So this definition is saying that if we have two y values on this graph that are equal to each other, supposing this y value over here and this y value over here is equal because they lie on the same horizontal line, then this is going to be one-to-one if and only if their x values are equal to each other. But in this case here, we clearly see that this x value here is not the same as this x value here. And what this tells us is that this function is not one-to-one. On the other hand, on this red graph over here, if we find any y value here, we see that it's only associated to one x value here. And if we had another y value that was equal to this y1, then it would have to also be associated with the x1. And so this function is in fact one-to-one, and that's because all the y values on the graph are unique. So the example on the right-hand side is where the idea of the horizontal line test came from. So let's go ahead and just recall the horizontal line test. And the horizontal line test states the following. A function is one-to-one if and only if no horizontal line intersects the graph more than once. So let's go ahead and look at an example. Example number 1. Determine if the following is one-to-one. And our graph is given by the following. So let's go ahead and apply the horizontal line test. And so what we need to do is we just need to find at most one horizontal line that intersects this graph more than once, and this is not going to be a one-to-one function. So we'll go ahead and just start at random points and go throughout the graph. So this line's fine, this line is fine, but then finally we get to this line here. And we see that this line intersects the graph in more than one point. In fact, it intersects it in an infinite number of points. And what this tells us is that our graph fails the horizontal line test. And what this means is that our function is not one-to-one. All right, so let's go ahead and try another example. This time we'll do a more algebraic problem. And what we want to do is we want to determine if the absolute value function is one-to-one. Recall that the absolute value function is a piecewise function, and so this is defined to be the following. It's going to be equal to x if x is greater than or equal to 0, and it's going to be equal to negative x if x is strictly less than 0. And this function is not going to be one-to-one if we can find a y value that has two different input values for its x values. So for example, let's go ahead and look at the absolute value of 1, and we'll go ahead and look at the absolute value of -1. So the absolute value of 1 is just equal to 1 itself, and so the output is 1, but the input here is also 1. And very similarly, by the definition of the absolute value function, the absolute value of -1 is 1, and again, this is our output. Our input, though, was this -1. And so what we just found was two different x values that go to the same y value, and so the assignment in this function is non-unique, which means that our absolute value function is not unique. Oh, sorry, it's not 1-to-1. Now, if you did want to do this graphically, you could just go ahead and check the graph. So on the right-hand side, we have the positive part of our piecewise function, and on the left-hand side, we have the other part of our piecewise function. And if we just apply the horizontal line test real fast, we could see that we could find a horizontal line that intersects this twice, and so this fails a horizontal line test and is in fact not 1-to-1. So we just confirmed that the absolute value function is not 1-to-1. Let's go ahead and try to show that a function is 1-to-1 using the definition. To show this is 1-to-1 by definition, we need to start off with the following. Given any two x1 and x2, if we evaluate the function at f of x1, and this is equal to f of x2, what we need to show is that this implies that x1 is in fact equal to x2. So let's go ahead and evaluate our function at x1 and x2. This is going to give us that x1 cubed plus 4 is going to be equal to x2 cubed plus 4. Subtracting 4 from both sides, we get that x1 cubed is going to be equal to x2 cubed here. And this next step is rather important. So let me just go ahead and write out what I'm going to say. Basically, what this is saying is that if two numbers have the same power raised to the third, then they're in fact the same number. This does not occur for even powers, only odd powers. Okay, and what this means then is that x1 was actually originally equal to x2. And so the assignment of inputs to outputs is in fact unique.